Hello, my name is Thomas Lemberger, and the next 20-something minutes I'll present to you our latest research on incremental verification. It's called difference verification with conditions. I'm the guy with the glasses on the right. This is joint work with Marie-Christine Jacobs from TU Darmstadt and my supervisor Dirk Bayer. So let's get into the context of the work. We have some program P, and we want to make sure that some property holds on it. Usually this is something like the assert, or there's no failing assert, or a certain value never gets greater than 0, or we don't have a division by 0, etc. We want to have this automatically checked, just like testing, but actually a proof. And to do that, we use an automatic verifier. We give the program and the property that we want to check against this program to the automatic verifier, and he tells us after some computation time whether the property holds or does not hold. If it doesn't hold, usually there's a bug. Now we are software developers, and this means that our software develops. So we do have some modification to our program after some time, for example, a bug fix, some refactoring, there's a change request, or some new feature that we implemented. And now we want to check again that the property holds on this new program P prime. We run our verifier again, it takes some time, and we get a result. And this continues. Every single modification we want to check that our program is safe. And we want to do that so that we have a continuous integration, that we always know when a bug is introduced. But this has multiple challenges that don't occur in testing that often. First, the verifier takes quite some time, or may take quite some time, to verify a program. This means that if modifications come faster than the verifier can find the solution to a task, then we can't use verification continuously. And then the verification is infeasible. So let's look at an example for this. We have some program P. You don't have to know the specifics about that, but it has two branches, an if branch and an else branch. The if branch is quite complex to verify. Let's just assume that there's a while loop, and verifiers usually have a hard time dealing with while loops. The else branch is only two arithmetic operations. That's quite simple. And afterwards we have an assert. So we give this to a verifier, and the verifier tells us if you take the else branch, there's a bug. And line 5 actually is a bug. So we fixed this. Now line 5 is correct and our program is correct. We want to check this program again, and this means that we rerun our verification on the whole program again. But actually this is not necessary because we only changed the else branch. The if branch stayed as is. There's no need to re-verify that because our modification had no impact on the if branch. We visualize this with this small Venn diagram. We have executions of our original program P, xp, and then we have all of the possible executions of our new fixed program P prime on the right. And some executions exist in both programs. Executions that go into the if branch in program P are exactly the same executions that happen when the execution goes into the if branch in program P prime. Only the else branch is different and outside of the left circle. So actually we only have to re-verify this, and re-verifying the unchanged program executions wastes resources. So even if the verification task is fast enough to do continuous integration, it is better to just reuse information that was obtained in a previous verification run to speed up later verification runs. And this concept is called incremental verification. It's already been around for quite some time, and there are some great techniques that tackle this challenge. The idea is that you don't just use any verifier, but you use an incremental verifier that gives you the result, but also some information for later verification tasks. And any later verification task then can use that information to speed up the next verification of the new program version. This information can be manifold. It can be function summaries, invariants, some caches that are used, for example, for solving formulas, etc. But these techniques usually have some weaknesses. Existing approaches often require an initial verification run, which is infeasible for large existing systems and sometimes unwanted. The existing approaches require the same verifier in each step, often, not always, but often. This means that we have to decide for one verifier at the very beginning. So let's say we use infer from Facebook, which has been used for continuous integration quite successfully. But now we find out that they stopped development for some hypothetical reason, and we want to switch to a new, still developed verifier. So we can't do that with the current infer approach, but we would have to re-verify the whole program with the new approach again at first. And last, often, even if techniques are not tailored to one tool, they are tailored to specific verification approaches. For example, a technique may use some information that only exists in symbolic execution. So of course it can only be used with symbolic execution and not with other verification approaches. Our technique, difference verification with conditions, wants to change that. We do not require an initial verification run, so you can pick up difference verification with conditions at any point in your development process. We do not care about switches between verifiers. We don't even know about them because the concept doesn't work that way. And last, difference verification with conditions is independent of any specific verification approach. You can switch verifiers whenever you want, and you can use whatever verifier you want. How do we do that? Instead of using some information exchange between the verification runs, we use a verifier-independent condition to exchange information. And we construct these conditions not from a previous verification run, but from an original and a modified program. We extract the differences between these two programs, put them in a condition, and give this to the verifier. So let's see how this works. These conditions are based on some existing concept called conditional model checking. And the idea of conditional model checking is that you don't just get a program and a property, but also a condition that guides the verifier. So a conditional verifier that understands this condition can then use it during the verification run to only look at those program parts that the condition deems interesting. So the condition restricts the relevant state space of the program. It does so with two different mechanisms. The first mechanism is source code guards that restrict the syntactic paths. So the condition can tell the conditional verifier, hey, there's an if and an else branch. Do not look at the if branch, only look at the else branch. And the second technique is state space guards that restrict the possible program states. So the condition could tell the conditional verifier, if you take the else branch, assume that x is greater than 0. Let's look at an example. We have our modified program p prime on the left, and we want to tell the verifier to only look at the else branch and ignore the if branch. So our condition starts with an initial state q0, and it tells the verifier, if you encounter line 0 with statement r equals 0, go to state q1. And this is a source code guard. It tells the verifier what to do if a certain syntax line, a certain source code line is encountered. And at q1, it gets interesting. There's the differentiation for the if branch. So the one path to the left says, if you are in line 1 and you see the assumption a less 0 and follow it, which is the if branch, then go to Q2. Q2 is a sync state. It does not have any outgoing edges, and it is not an accepting state. This tells the verifier to stop exploration because it's not possible to reach an accepting state anymore. But if the verifier is in line 1 and encounters that a is not less than 0, the source code line, which is the else basically, then it goes to Q3, and from there, when it encounters line 5, which it does immediately afterwards, it goes to the accepting state Q6, and the accepting state tells the verifier to analyze everything starting from there. So at line 5, the verifier will go into Q6 and will verify everything that comes afterwards. In this example, we only look at source code guards because we only considered these in this work, but in theory, it's also possible to use state space guards as well. So we need some difference condition generator that generates this condition that tells the verifier where to go. And as a formal concept, it's defined through its inputs and outputs. So it gets a program and a modified program and outputs the condition that tells the conditional verifier about the difference. And one property. The difference condition generator, however it is implemented, has to fulfill a soundness criterion for the verification to be sound. And that criterion says that the created condition does not exclude any modified executions. That is, if you look at all of the executions of the original program and the modified program, it is not allowed to exclude any of the new executions of P prime. Because otherwise, we may exclude an execution that leads to a property violation. So let's plug this together. We have a program and a modified program. We give these two to a difference condition generator that creates the difference condition. And we give this to a conditional verifier that uses it to only analyze those parts of the modified program that differ from the original program. Now, I'm not sure how many of you already knew that concept of conditional model checking and conditional verifier, but there are not a lot of conditional verifier around. I only know of one. So since we want to achieve the goal that any off-the-shelf verifier can be used for this approach, we resort to another technique that we researched called reducer-based construction of conditional verifiers. So we take any off-the-shelf verifier and turn it into a conditional verifier by using a so-called reducer. The reducer takes the condition and the input program that should be analyzed and merges them into a residual program. And this residual program only contains those program semantics and those executions that are not excluded by the condition. This can then be given to any off-the-shelf verifier to only analyze the remaining program paths. So let's look at an example for a difference condition generator. This is a quite simple implementation called diffcont, and it's based on the syntactic differences. So diffcont works in two steps. In the first steps, it detects the syntactic difference by computing a parallel composition of the original and the modified program. And if it encounters any difference in this composition, it stops because it can already tell there's a difference and it will propagate downwards. So let's look at an example. We have our original program and our modified program as we already know it. And we create this composition. We start with the first line in both. First line is the same in both, so we can continue. We have the if statement. And we go into the if first. So we say we encountered in line 1 that a is less 0. Now we describe the while loop. This is lines 2 to 4. and going out of the while loop, which jumps to line 7 because we're at the end of the if, and we go to the point after the if, and there we have an assert. So this is everything that is reachable, syntactically reachable from the if branch. Now we go to the else branch. And here we immediately encounter the modification in line 5. So we stop our composition here, and to mark this as a change, we only store the changed location, not both of the locations. Once we have this, it's easy to generate a condition from it. We collapse all of the unmodified changes because we don't really care about these. We can just exclude the uppermost of them, which is L2. And then we turn all of this into a condition as we already saw. And our change is the accepting state from which everything reachable should be analyzed. So because diffcont only works on the syntax of a program and is quite simple and straightforward, it also has some conceptual limitations. And that is that modifications propagate through the program. So if there's some change to a global variable or a big loop around the program, that propagates the modification. Let's look at an example here on the right. We have the new program p infinity, which is basically the same that we already saw before, but there's a big while loop around the existing code. And this means that if we change line 6, which is the location that we changed before all the time, this time it will not only affect the else branch, but it will propagate through the loop back to the top of the loop and into the if branch. So in this case, we would have to re-verify everything, even if we only change the else branch. So diffcont works best on loosely coupled systems that contains distinct features that do not interact very much, or object-oriented systems, or things like the strategy pattern. So last, let's look at how well our approach performs. To do that, we compared the full re-verification of programs to the difference verification with conditions. And we use two different comparisons. First, we use a native conditional verifier to see how well our approach would work if we had a conditional verifier that actually makes use of the condition. And second, we use an off-the-shelf verifier that we turn into a conditional verifier with the reducer-based approach that was mentioned before. We implemented diffcont and difference verification for C programs. If you're interested in the data or how to run the tool, you can take a look at our artifact. And for the comparison, we used the state-of-the-art framework CPA checker with predicate abstraction. This can understand conditions, so it is a native conditional verifier, and two verifiers that do not understand conditions, CPA-sec and Ultimate Automizer. We chose these based on their performance in SVComp. And our evaluation environment is very similar to that of the big software verification competition SVComp. That means that we use 15 minutes time limit per run and a memory limit of 15 gigabyte. Last, I want to take a minute to talk about the tasks that we used for our evaluation. And these we created artificially. Each task is a tuple of the original program P and the modified program P prime, and the task is to verify P prime. The original program P is a combination of two strongly coupled programs from the SV benchmarks, which are the benchmarks that are used by SVComp. We had to create these to get some programs that are loosely coupled to make use of diffcont, because if we only look at the strongly coupled programs that we have for SV benchmarks, we won't see any good results because the programs are too specialized and do not represent real-world big systems that contain independent components. So we used the main methods of the two original programs. Here we call it main 1 and main 2. And we created a new program by joining these. We have a new main method that non-deterministically calls one of the two. So there's no interaction between the components. And then from these original programs, we created modifications by using existing modifications in the benchmark set that already existed. These modifications can be bug fixes, it can be the new introduction of a bug, or that a program was already safe and stays safe after the modification. When we perform re-verification with the native conditional verifier, we can see that difference verification with conditions yields a big benefit. So in the scatter plot, we see the CPU time per task that was taken by predicate analysis in CPA checker and with difference verification. So on the x-axis, you see the full re-verification of the program, and on the y-axis, the verification with difference verification that only verifies the changed part of the system. Everything below the diagonal, difference verification with conditions performs better. Everything above, it performs worse. And everything at the edge either is a timeout or some error occurred. So this shows us that for the vast majority of tasks, difference verification with conditions performs significantly better than the full re-verification. Unfortunately, this looks different when we use off-the-shelf verifiers that we turn into conditional verifiers. So here we see the results for CPA-sec with full verification on the x-axis and uAutomizer in the second graph. And again, difference verification on the 2 y-axis. And here we can see that below the diagonal, there are still a lot of tasks that we perform better, that our approach actually has some benefit. But there are also a lot of tasks where we perform worse. And we have to make the reducer-based construction of the conditional verifier responsible for that, because it completely changes the structure of the program. So we hope that once the reducer-based construction of conditional verifiers improves, this technique automatically improves with it. To conclude, we presented the concept of difference verification with conditions that does not require any initial verification runs on big systems. It allows changing the verifier at any point in the verification process during software development, and it is independent of any specific verification approach. So developers are able to use any verification approach in any implementation that they want, and they can change that at any time. For this concept, we showed an example implementation that we call diffcont, which performs difference computation of an original and a modified program based on their syntactic difference. And last, we showed through a big evaluation that our approach actually yields a significant benefit. Thanks for your time.